Alrighty. Happy Friday, everybody, and we are coming to the end of this diffusion paper week. We've been looking at diffusion papers the entire week, and this is the crown jewel here. This was released this week, and it's called On Distillation of Guided Diffusion Models. This is a heavy hitter paper here. You have Kingma. These are some RL royalty here. This is a collaboration between Google Research, Google Brain. You have Stability AI people. You have Stanford University people. So there's a lot of heavy hitters here. So hopefully we'll be able to take everything we've learned and all the different nuances that we've started to pay attention to when it comes to diffusion models and see what these guys have to say about it. Alrighty, so big picture here to start, big figure with a bunch of cool looking images. They say distilled stable diffusion samples generated by our method. Our two-stage distillation approach is able to generate realistic images using only 1 to 4 denoising steps. So this is huge. We saw yesterday there was a table on the paper. Yesterday we read a paper for Paella, which is a I don't know if I want to say community, but it's a diffusion model that was really trying to push the speed, and one of the ways that you could make these models faster is reducing the total amount of denoising steps. And they were showing how previous models can take 1,000 denoising steps. So here now you see how a different group of people has also found a way to drastically reduce that by a couple order of magnitude. So 1 to 4 denoising steps is definitely impressive. Compared to standard classifier-free guided diffusion models, got a little Boo here is being a little. Boo, do you have something to say? No, she doesn't. So, again, classifier-free guided. This was the situation where basically you perform inference twice. Right? You perform inference once and you remove the noise without conditioning the diffusion model on anything. And then you perform inference again, conditioning the diffusion model on, for example, text embedding. And then you have this parameter that allows you to kind of interpolate between a completely unconditioned generation and a conditioned generation. Classifier-free guided diffusion models have been shown to be highly effective. Large-scale diffusion frameworks, including DALI 2, Stable Diffusion, and ImageGen. Downside of classifier-free guided diffusion is that they are computationally expensive at inference, since they require evaluating, 2 diffusion models, a class conditioned model and an unconditional model. Right. To deal with this limitation, we propose an approach to distilling classifier-free guided diffusion models into models that are fast to sample from. So distillation, this word is used to describe methods that try to, for example, dataset distillation is something that I've seen before, and that's taking a large dataset and trying to figure out how to reduce it by several order of magnitudes and distill it to a kind of core data set that if you train on that distilled data set, you still get roughly the same performance as training on the original data set. So that's what distilling means in the context of data set. In this case, distilling probably means using a larger model to train a smaller model, so kind of a teacher-student paradigm there. And the smaller models are going to be faster, and hopefully you try to get them so that the performance is as close as possible to the bigger models. So overall, the theme of this paper might be kind of speed again, so similar to yesterday's paper about trying to make these diffusion models faster, and we see how that's kind of an important thing for the machine learning research, specifically diffusion model community, because to make these things, to productize these things and eventually monetize these things, you really want them to be snappy and quick. So a lot of people are spending a lot of time thinking about how to do that. In a pre-trained classifier-free guided model, we first learn a single model to match the output of the combined conditional and unconditional models. And then we progressively distill that model to a diffusion model that requires much for training steps. Yeah, so this is the distillation. For standard diffusion models trained on the pixel space, our approach is able to generate images visually comparable to the original model using as few as 4 sampling steps. These are kind of bogus data sets, so get our highlighted color for data sets here. ImageNet 64 and CFAR 10. So this is ImageNet 64 by 64 images. So these are kind of very, very grainy little thumbnail images. And then CFAR 10 is the same thing. It's also kind of these grainy little thumbnail images. Yeah, so that's what CFAR 10 looks like, right? It's very, very grainy, low quality, but the reason people use them is because they're fast and you can train relatively quickly. Achieving Fréchet inception distance. So again, this is kind of the controversial metric we've been seeing in all the papers this week that looks at the distribution of generated images and the distribution of, for example, COCO or real or other kind of real image data sets, and then compares them that way. But as we saw throughout this week, there's contention as to whether FID is a actual valid metric. And I think the gold standard is what we saw in the first paper this week, the generation of dance, where you actually pay for a study where you get a bunch of people to look at image A and image B and then tell you which one they think is better. So I think that to me is the gold standard. For diffusion models trained on the latent space, e.g. stable diffusion, our approach is to generate high-fidelity images using as few as 1 to 4 denoising steps, accelerating inference by at least 10-fold, compared to existing methods on ImageNet, 256 by 256, and Laon dataset. So, and let's include the word ImageNet. So, another thing we've seen this week is basically these diffusion models. Diffusion models are basically during training you're adding noise, and then during inference you're removing noise, and you're basically learning this function that removes noise iteratively, right? In step by step. And you can either remove and add this noise directly in the pixel space, which is what they're saying here in this first part, or you could remove and add this noise in the latent space, right? So you first take the image and you encode it into a smaller embedding, right? So an image might be 256 by 256, but then you compress it down into a little embedding, and then that's where you do your noising and denoising. And this allows you to do things faster, because if you were going in pure pixel space on a 256 by 256 image, it would take much longer. Okay. Denoising diffusion probabilistic models, DDPMs. This is kind of the official name of models. I've achieved state-of-the-art performance, blah, regular generation. Classifier-free guidance further improves the sample quality of diffusion models and has been widely used in large-scale diffusion frameworks. However, one key limitation is its low sampling efficiency. It requires evaluating 2 diffusion models to generate 1 sample. limitation hindered application in real world setting. That's the key word right here, is that these diffusion models are working very well, to the point that a lot of people are very hungry to productize and monetize these. So as soon as you start thinking about putting these out in the real world and putting them behind an API and having people pay for these, latency and speed and user experience start to be the metrics that you want to improve, right? So that's what all these research groups are working towards. Okay, in the first stage, we introduce a single student model to match the combined output of two diffusion models of the teacher. Okay, so it is this kind of teacher-student paradigm. Then we progressively distill the model learned from the first stage to a fewer step model using the approach introduced. Using our approach, a single distilled model is able to handle a wide variety of different guidance strengths. Guidance strength, again, is the weight, right? The hyperparameter that you're using to interpolate between either the classifier-free or the context-free or the context on. So like, if you have a guidance strength of 0, it's just going to be generating entirely from the context conditioned vector. And if you do it guidance strength of 1, it's going to not use it. So in the previous paper, we've seen W used as the variable here. I don't know if that's what they'll use here. Wow, there's a lot of math here. I think they actually use W. Maybe they do use W again. Might be a different W. But hopefully the notation is consistent. We don't have to keep relearning different notations here. Our distillation framework can not only be applied to standard diffusion models trained on pixel space, but also diffusion models trained on the latent space of an autoencoder. Right. So for pixel space, they use the smaller data sets. And then on the latent space, they use the larger data sets. And then they take their model that they're talking about here, and then they show you how it performs on kind of the standard set of generative tasks, such as text-guided image inpainting and text-guided image editing. Okay, so they are using the W for the guidance weight. One sampling step. That's pretty crazy. Okay, background on diffusion models. Good. Like this expected value here. Look how many terms there are in this subscript. Okay, so we have samples X from a data distribution P data X. Go ahead. We have samples. We have our data distribution. We have our noise scheduling functions, alpha t and sigma t. We train a diffusion model x hat theta. I would say parameters theta, right? Theta is not just one parameter, it's a lot of parameters. And then they're minimizing via the weighted mean squared error here. So the expected value at t sampled from 0 to 1, x sampled from this p data distribution, z sub t sampled from a q, which is conditioned on x and gives you z sub t, omega, or w here, which is the guidance weight, and this here is the difference between your z sub t is probably the latent. No, z sub t, z is the noise. So x hat theta removes the noise, and you want to compare that to the original image. So this is the actual image, and then this is the diffusion model's output, which is the removed noise of the previous time step. And then you have here a L2 loss, so squared difference. Lambda t is the log of alpha squared t over sigma squared t, and this is a signal to noise ratio. Okay. So your noise scheduling. So again, we've seen in these diffusion models, the noise that gets added over the training period and then removed, that noise is not the same at every single time step. There's now kind of a bunch of stuff that people are doing with these special noise scheduling functions. So they'll have a couple different hyperparameters in there that they use to kind of shape the way that this noise gets added and removed. So that's what these two hyperparameters are here, alpha and sigma. Q z of t given x is a normal distribution centered on, or no, here you go, centered on alpha tx and sigma ti. So this is the variance here. Sigma is a hyperparameter for the noise scheduling function that affects the variance, and then alpha is a hyperparameter for the noise scheduling function that affects the mean of this normal distribution, this normal noise, this Gaussian noise. And here you have W of lambda t is a pre-specified weighting. Okay, so this is interesting too, where I think in the previous papers we saw how this W, this guidance weight W, was just a number that you could choose, but here they're going to make it a function, have a weighting function. Maybe there's kind of some clever scheduling that gets applied there as well. Once the diffusion model is trained, one can use discrete time DDIM sampler to sample from the model. Specifically, the DDIM sampler starts with noise and updates as follows. N is the total number of sampling steps. Here you have Z sub S is kind of noise hyperparameters here, alpha and theta, where S is basically S is going to be the current time step minus 1 over n. So it's this is just a normalized time step. So if you have 4 steps rather than having 1, 2, 3, 4, you're going to have 1 minus 1 over 4, so 0. 2 minus 1 over 4, 0.25, 0.75, and then 1. So S is just the normalized time step from 0 to 1. And here you have Z sub t, previous time step, the denoising. Classifier-free guidance is an effective approach shown to sample quality. Specifically, it introduces a guidance weight parameter, W, greater than or equal to 0. Kind of interesting. They're saying that the dimensionality of this guidance parameter is greater than or equal to 0. I don't know what equals 0 means. To me, in the previous papers, we've seen this guidance weight parameter just be a single number, so the dimensionality of that would be 1. But here, they're kind of hinting that it's going to be a little bit more clever than that. So the classifier-free guidance evaluates the conditional diffusion model, where C is the context, right? So this is your text embedding, or class label, or even image embedding. And then you have your unconditional diffusion model, x hat theta, and this is the weighted, or the interpolation that we were talking about here, where you're using W to interpolate between the context-free and then the context. Progressive distillation. Our approach is inspired by progressive distillation, an effective method for improving the sampling speed by repeated distillation. Well, now this method could not be directly applied to distilling classifier-free guidance models other than the deterministic IM sampler. Solve these shortcomings. Increase the latent diffusion models, so so this is the key insight here, is that latent representations are usually of a lower dimensionality than pixel space. So adding and removing noise and doing inference and everything that you do, is if you do it in a latent space, it's going to be smaller and it's going to be faster. And especially because you have access to super resolution models, you can just take your final image and make. I'd actually be curious, because I wonder if you take your image and just compress it down to a smaller image using just kind of standard image compression, right? Low resolution versions of the big image, and then diffuse in that space. So it's still pixel space, but it's a kind of reduced form of your pixel space. I wonder what happens if you train something on that versus if you train something on a latent, right? What is a better compression of the content in an image? Is it an encoded or a pre-trained encoder, or is it just the image itself but downscaled? We applied distillation, so they apply it to both pixel space and latent space. Given a trained guided model, either the pixel space or approach can be composed as 2 stages. So there's 2 stages here. First stage, we introduce a student model. I think that's Ada, right? Yeah. Greek letter Ada. So x hat sub Ada 1 of z of t, which is the latent or the image, depending on which, or the pixel space or latent, and w, which is your guidance vector, with a learnable parameter Ada 1. It's parameters, I would say, right? I don't know why these are models, right? These are neural networks, and the neural networks have a lot of different numbers within them. There's weights and biases, and I don't know why they keep using the singular parameter rather than parameters. Maybe it's because they're like, hey, at the end of the day, theta is just some tensor of parameters, so you can just say that it is a parameter itself. It's just a higher dimensional parameter. Match the output of the teacher at any time step. Student model can be either a continuous time model or a discrete time model, depending on whether the teacher model is. Assume both the student and teachers are continuous, as the algorithm for discrete models is almost identical. So, I mean, this S here that we saw, S equals t minus 1 over n, this normalized version of the time step, I think maybe that's what they're talking about here between in continuous versus discrete. Optimal guidance strength is often a preference. given a range of guidance strengths. So you have a couple different possible guidance strengths here with a min and a max. We optimize the student model using the following objective. The expected value of the guidance strength from a probability distribution of guidance strengths. This capital U here means uniform. So the guidance strength is sampled from a uniform distribution that spans the minimum and the maximum guidance strength. The time itself is sampled from a uniform distribution between 0 and 1. And then your X is sampled from the data distribution over X, which is basically just your image data set. That's what P data is the distribution that is represented by your data set. And the expected value is of the L2 loss, right? So the squared difference between your student teacher here and then your student model and then your teacher model at the same W. Note here that our distilled model is also conditioned on the context C, but we drop the notation C in the paper for simplicity. We provide the detailed training algorithm in algorithm 1. To incorporate the guidance weight W, we introduce a W condition model where W is fed as an input to the student model. Better capture the feature, we apply a Fourier embedding to W. Okay. See what that means. As initialization plays a key role in performance, we initialize the student model with the same parameters as the conditional model of the teacher, except for the newly introduced parameters related to W. They're using a UNet. And the open sourced repository. Okay, so here they have the algorithm for the stage 1 of their two-step distillation process. So you have a trained classifier-free guidance teacher model, which I think is going to be the Stable Diffusion or the image gen model, right? This is they have the Stability AI guy that's on this, but they also have the Google Research. Stability AI is going to use Stable Diffusion. Google Research is going to use image gen. So have their data set D, which the X out of D sample data. I think to be consistent from a notation perspective, they should have said X sampled from P data of X, where P data of X is the data set. You have your loss weight function, W. I don't think that's loss weight function. Guidance weight function. And then while not converged, you have here you're sampling the data. Here you're sampling time, again from the uniform distribution. The one, you have the guidance is sampled from a uniform distribution of between minimum guidance and the maximum guidance. You have noise sampled from a Gaussian. You add the noise to the data, right? So you have your little hyperparameters here, alpha and sigma, and you're taking your image or your latent, depending on which one whether you're doing in a latent space or pixel space, and you're adding this Gaussian noise. Then you also have your signal to noise ratio, which is this lambda here, which is just a function of these two hyperparameters, alpha t and sigma t. which have their own functions that are probably decided and chosen by a human. So they're not learned. Then you compute, so this is the image, x hat w, so you're basically combining, right? This is with the conditioning, this is without the conditioning. See, the difference here is that c. So you're using this, the w, the guidance weight, to basically combine those and interpolate between these. Compute target. Something, the indentation there is a little weird. Then you have the loss, is this w. Oh no, it isn't. No, so these are two different w's. This is an omega, and this is a guidance weight. So the guidance weight is w, but then you have weighting function omega. All right, there we go. So the weighting function basically just is a function of this signal to noise ratio. So, okay, so the loss here, the loss that you're going to be using to improve your model, your student model, right, which is parameterized or specified by this eta, right? And here, this is the actual gradient step that they're taking, right? So they're taking a gradient step on the weights eta, the weights of the student model, which are eta, because this signal to noise ratio is going to change as a function of the time, right? Where along the progressive addition and removing of noise you are. That means that the loss function should also be weighted according to that, right? Because the kind of magnitude of these things is going to be different because you're adding different amounts of noise. So therefore, you kind of want to adjust the loss accordingly. So that's what this weight function, loss weight function, is really doing. And here you just have the squared difference between the student and the teacher. Okay. So stage one is about basically taking your student model, which they say here they initialize to be basically the same as the teacher, and then making it converge towards the teacher. Second stage, we consider a discrete time step scenario and progressively distill the learned model from the first stage into a fewer step student model with a learnable parameter eta 2 by halving the number of sampling steps each time. Let n denote the number of sampling steps. Omega or W equals the guidance weight sampled from that uniform distribution, and this is the actual discrete time steps. So total number, this is the current step over the total number of steps, and this is current step minus 0.5 over the total number of steps. And after distilling the two n steps in the teacher model to n steps in the student model, we can use the n step student model as the new teacher model. Okay. At each step, we initialize the student model with the parameters of the teacher. Okay. So this is what they mean by progressive distillation, is that they're effectively taking these models, right, taking a model that maybe has hundreds of denoising steps, and then training a student model that tries to do the same thing, but in half the amount of steps, 50 steps. And then once they train that student model, that again is the same size and has the same parameters initially as the teacher model, that does it in half the steps, then they'll make that one the teacher, and then they'll make a new student that tries to do it in the half of the steps of that. So that's kind of this progressive distillation process. And if you run that a bunch of times, right, you keep having the number of steps, and eventually the goal is that maybe you can do it in one step. N-step deterministic and stochastic sampling. We note that given the distilled model, this sampling procedure is deterministic. Okay. Given the initialization. In fact, we can also perform n-step stochastic. We apply one deterministic sampling step with 2 times the original step length, and then perform one stochastic step backwards, perturb with noise. Where your noise here is coming from Gaussian. Okay, so these are all just different noises here, right? So you're adding the noise to your data. So X is the raw, uncorrupted data, and then Z is the data once you've added the noise to it, right? Where data is either an image, which means pixel space, or it's a latent vector or image embedding, whatever terminology you want to use. So all of these equations here, they're basically using these little hyperparameters such as alpha and sigma to accidentally highlighting everything. They want to add actual noise in there, right? That's kind of what they mean. Stochastic is just another way of saying random, and then deterministic is another way of saying known, not random. So they want to have some noise in here, right? So they're kind of like doing these like combined sums of actual noise here and the noise that already exists, right? The deterministic noise. It's just like very dense. H equals t minus 3 over n. K equals t minus 2 over n. And S equals t minus 1 over n. Okay, so this might be what they're calling the Fourier. We saw that in the, where was that? The introduction. But they mentioned that they were doing Fourier noise, or something they called. Here we go. Okay. Yeah, we apply Fourier embedding to W, which is the guidance weight. Never mind, that's not what they're doing here. But right, this number here, 3 over n, 2 over n, 1 over n, that kind of like is reminiscent of kind of like a Fourier series, right? Where you're kind of adding these terms that are each progressively smaller. I don't really understand what's going on here, to be honest. I mean, these people are heavy hitters, right? Kingma, like these guys from Google Brain, like these guys do not mess around. Like they know their statistics very, very well. So like this 500 IQ thing they're doing here with the deterministic and stochastic sampling, I feel like only they really understand why and really what that is doing. They evaluate the performance of our distillation approach on pixel space and latent space, and then they further apply their approach to text-guided imaging. Okay. In this experiment, they consider class conditional diffusion models directly trained on the pixel space. focus on ImageNet 64 by 64 and CFAR 10. So this is the small images for the pixel space tests. This is the guidance weight min and max, so it's a uniform distribution over this, so they can randomly sample anywhere between 0 and 4. So these are different forms of noise sampling. To better understand how the guidance weight, we also include train models using a single fixed W as a baseline. Okay. FID and inception scores to evaluate. And then they say that their distilled model is able to match the teacher. I think match the teacher performance is difficult to say, but it depends on whether you think FID and inception scores are valid. The prediction teacher model tends to perform better than the Sigma prediction model. We fine-tune the open-sourced Sigma prediction models in prediction. Okay, so the way that these diffusion models remove noise is that they're predicting the noise and then removing it, right? Where sigma here is, lowercase sigma is the noise, so you have sigma prediction, predicting the noise, or V prediction. So do they specify what V is? Doesn't seem like they tell you what V is. Okay, so we don't know what V is, but it's different from the sigma prediction. Class conditional generation. I feel like this is unfortunate terminology, because it used to be that these, I think when they originally came up with this term, they were conditioning the diffusion models on a class, right? So you would condition it on dog or cat or car or airplane, but that's not really what people are conditioning these diffusion models on anymore, right? They're conditioning them on contexts, or on which is like an embedding. It's like a vector that represents text. So I would almost say that a better name for this would be context conditioned generation. Okay, we start from the DDIM teacher model, 512 sampling steps, right? So that's 500 steps is what they're starting with, which I think might be what latent diffusion or what stable diffusion does. This is the strength here that they're using for the latent version of this. So in the pixel space, the guidance weight is uniform between 0 and 4. in the latent space, they're using a guidance strength of between a uniform distribution between 0 and 14. Find that our distilled model is able to match the performance of the teacher model in terms of ID scores. 2 to 4. So they go from 512 sampling steps to 2 to 4 sampling steps. Wow, what a name. Total of 3,000 gradient updates in their stage approach. They have a slightly different guidance weight here between 2 and 14. Applying progressive distillation for 2,000 training steps per stage, except when for the low step regime. Okay, so this is interesting. They're training longer once they get to the small amount of steps, right? Once they're trying to go from 4 steps to 2 steps. But when they're going from 512 steps to, say, 256 steps, they're using less training steps for that distillation process. So there's a lot of magic numbers here, right? The guidance weight bounds, the number of updates. And I really wish they would have kind of maybe talked about how they found these hyperparameters. I'd be curious if these are just coming from intuition, right, that these researchers have built over their careers, or whether they've just literally done a huge hyperparameter search and they came up with those numbers from there. Results. We present samples in figure 4. Go to figure 4. Here we go. Text guided generation on Laon. So this is 512 by 512 images. Using our distilled diffusion model. Our model is able to generate high quality image samples from 2, 4, or 8. So this is the student model, which has been progressively distilled from basically stable diffusion. Stable diffusion would have created these images in 512 denoising steps, and this is the student model progressively distilled and then performing 8 denoising steps. So these are very high quality. And then you see they do another step of this progressive distillation and try to get it to do half of the amount of steps, so 4 denoising steps. You're still getting very high quality, except there's a little bit of a hint, right? The eyes on this minion, the eyes on this like tunified Harry Potter, like that there's starting to be, the cracks are starting to show. And then if you do another step of progressive distillation to the point that your student model is now just performing 2 denoising steps, you're still getting like semantically meaningful images, like there is stuff here, but you are starting to notice these artifacts, right? Like the mouth here of the Einstein, whatever this little green blob is, you are starting to see some of these artifacts that come up with these diffusion models, or the generative models. We evaluate CLIP and FID scores to assess text-image alignment and quality. So CLIP, again, is a contrastive language image pre-training. It's basically learning an embedding space where you can map corresponding text and then images, and then you can look at the distance between those. So text-image alignment, what they're basically doing is they're going to feed in this image, and then they're going to feed in the text that was used to generate that image, and then they're going to ask how far away are the resulting CLIP latent spaces for the image and the text from each other. And then if they're close, that means there's a high text-image alignment. If they're far away, that means the clip doesn't think that the image and the text are similar or close together. So I kind of like that as a way to determine quality. So this is the specific clip that they're using. Their VIT is the vision transformer. So clip doesn't use, I guess this version of clip doesn't have a convnet. It's encoding the raw image into a latent space using transformers, which basically take the image, cut it up into these little patches, and then feeding each of those patches so that it's a sequence. Quantitative results in figure 9. When considering corresponding samples, we can observe a stark difference in visual image quality. Two-step samples. Shoot for the moon. You can observe a stark difference in blah, blah, blah. Here you go. All right, so we've kind of learned over the course of this week to not trust FID, and here they do have a sentence also saying that they don't really fully trust FID, so they do not fully capture the differences. Okay, depending on the exact implementation, batched versus sequential network evaluation, this decreases peak memory or sampling time. So the way that GPUs work, right, you can perform inference and you're going to have your model loaded on your GPU, and then you're going to load in your input image or your text, and then you're going to, like, that GPU is going to kind of crunch all those matrix multiplies. But the whole point of the GPU is that it can do a whole bunch of these matrix multiplies at the same time, right? It's so a lot of times, or not a lot of times, it is the fact that a batch of images will be much more efficient per image in terms of inference time than one image at a time. So they're kind of saying here that depending on how you implement this, right, it's actually much more memory and compute efficient to generate batches of images at the same time. Even though a batch of images is going to take longer than a single image, the batch of images per image is going to be better in terms of compute efficiency. Perform experiments on text guided using our distilled model. SD edit, which I assume is stable diffusion edit, which is SD. Play with that. Image synthesis and editing based on stochastic differential equations. SD edit allows stroke-based image synthesis. Okay. Sounds like a whole other can of worms, but we're just going to assume that it's just a edit with stable diffusion, but that's not all what it is. We perform stochastic encoding in the latent space, but instead use the deterministic sampler of the distilled model to perform deterministic decoding. We provide more analysis on the trade-off between sample quality, controllability, and efficiency. Okay, a different kind of subtask that you can do with these diffusion models is image inpainting. Image inpainting is you cut out parts of something, and then it, if they have a good picture of this, image inpainting, here you go. So you might take this picture of this apartment block and then mask, and then basically create this mask where you're saying this part of the image, I want you to inpaint that part of the image. So for example, they see here when they mask out this tree, it largely keeps the rest of the image the same, and it just kind of fills it in with the building. Here, they mask out the bottom half of the image, and you can see how it actually becomes a lot more creative here, and it either adds a lake to the bottom or trees or a beach. More masking. And I mean, this is really good. You can see how powerful this is. You can take the image, you can have someone sitting on a bench and remove the person on the bench. You can just have the person themselves, and then it'll automatically generate the background that is pretty consistent with the person. Before we skip, let's actually look at this here, table 1 and figure 5. ImageNet 64 by 64 distillation results for pixel space diffusion, right? So pixel space these are in the tiny little ImageNet and CFAR data set. So what does Frichet inception distance mean in a 64 by 64 image? Like, to me, that's just kind of starting to get meaningless there. We observe that training the model conditioned on a guidance interval performs comparably with training a model on a fixed W. I'm not even going to bother looking at those numbers. I just don't think they're going to get any insight from looking at that. And here, the graphs are basically these same numbers, but maybe more interesting version, because you can see the progression over time. So this is the number of sampling steps, right? So 512 is the number of sampling steps that Stable Diffusion does. So you can see that as you decrease the number of sampling steps, this is different guidance weights. So you have 0 guidance weight. FID, I think you want it to be lower. Yeah, FID lower is better. And then IS higher is better. So here you can see the 512 sampling steps. You have a higher IS, and then it slowly decreases. Interestingly, you see how this orange plot goes up for a second. So that's kind of interesting to me. This behavior right here, right? These other ones, it's like they're flat and then they go down. But the fact that this little bump here, that you go from 512 sampling steps to 128 sampling steps, and somehow you increase your IS, that means there's potentially performance to be gained by distilling. And they have different here: deterministic, stochastic, the single guidance weight, right, where they're not sampling the guidance weight from a uniform distribution. Different samplers, DDIM, DDPM. You can see how some of these actually explode. Some of them get better. The relationships change. So what I see here is that we don't fully understand this, right? If all these plots roughly had the same trends, then you could say, oh, there's an optimal value for W, there's an optimal sampler, you can kind of pick values for these hyperparameters and choose specific types of approaches. But the fact that there's such a variety here in terms of like the different behaviors, the fact that you can actually have things that go up and things that improve when you reduce the number of sampling steps, means that you're going to have to kind of pick these guidance weights or some of these other choices here, depending on your situation. What size is your data set? What exactly are you trying to do? Which subtask are you trying to do? because I think when you're ultimately when you want to productize and monetize these models, right, you want to reduce these hyperparameters. I think that realistically, you don't want people to be tuning these numbers, such as the guidance weight, right? Like your average person who wants to generate waifus doesn't need to know what the guidance weight is, and in fact doesn't want to know what the guidance weight is. So you want to hide those away from people. This is pretty cool. ArtStation painting. So this is what it starts with. Someone just like drew this in like Microsoft Paint, and then they applied the ArtStation painting kind of style transfer. They call this oh, actually kind of cool. They're using the Runway ML Inpainting model. Like all these figures are basically saying the same thing. They're basically saying we do things with less steps and it looks better or just as good. Aggressive distillation. And in this experiment, we explore distilling the encoding process for the teacher model and perform experiments on style transfer. Focus on pixel space. Perform style transfer between two domains, A and B. Okay, so they have two diffusion models, one trained on domain A and one on domain B. And as the encoding process, you encode with one and then decode with the other. The encoding process can be understood as reversing the DDIM sampling process. Provide more detail. Denoising diffusion implicit models. None of these approaches have achieved comparable performance. Okay, so these are other papers, other work that have used kind of a variety of statistical tricks here, exponential integrators, dynamic programming, which is more along the line of kind of improving the way that your GPU and your computer performs the inference, but then things like a probability flow sampler, fast SDE integrators, different tricks for making these diffusion models faster, but they say that their distillation approach is the best. How much you want to bet the progressive distillation paper? Jonathan Ho and Tim Salamans. Yeah, here you go, Jonathan Ho. Okay, so basically this Jonathan Ho guy is the progressive distillation guy, so really what this paper is they got Stable Diffusion's permission to get the progressive distillation guy to basically take his work and put it on top of these diffusion models. That's TLDR what this paper is. Deterministic sampling schemes versus stochastic sampling. Significantly speed up popular, but relatively inefficient. So, little tongue-in-cheek there, saying that Stable Diffusion is very popular, but it's written by scrubs. So, well, scrubs compared to these guys, right? Significantly reducing the cost of classifier-free guided diffusion models, our method will promote creative applications as well as the wider adoption of generation systems. But I bet you, despite all this democratization, you'll figure out how to put it behind a paywall and extract as much money as possible. State of technology. Okay, you have some appendices here, all the different algorithms. If else. Some pretty images. Text guided image generation. We compare our distilled model with the original model. Samplers here. Photograph of an astronaut riding a horse. So that's what you have here. You have different guidance weights. So 7 versus 12. 7, 9, and 12. You have, this is a different diffusion model. 2 steps, 4 steps, different numbers of steps. And yeah, I mean, their claims are true, right? Their model in just in the 2 steps actually produces meaningful results versus this DDIM 2 steps produces garbage. And it's garbage in an interesting way, right? These diffusion models, they start with noise and then they remove the noise. So it's garbage it looks like noise because that's what it started from. Similar kind of thing going on here. Okay, so here you have helicopters, you have castles, cars. Huge tables. Wow, they really like threw this is like all these algorithms, like who wrote these? Someone took the time to take all the code and then just convert it into LaTeX, or did they start with this on a whiteboard and then they just got some guy to convert it into Python? I'd be curious. Right, because I think at somewhere like Google Brain, you have specifically older researchers who are going to know how to they think in math space, right? They're thinking in this kind of space. But I think younger researchers tend to think in code space, right? They're thinking in Python. So to them, they write out the algorithm in Python, and that's how it makes sense to them. But if this was largely the brainchild or the kind of the idea of one of these older researchers who thinks more in like equations and math and handwriting, then they write it all down, and then someone has to interpret that into Python. Because a lot of times the like super mathy kind of whiteboard people aren't very good at programming. And then the people who are very good at programming aren't necessarily super good at super mathy whiteboarding. So just from like a human organization perspective where you have like a team of humans working on a problem like this, I think the interface between the kind of super mathy people and the programming people is kind of an interesting thing to look at. And I'd be super curious to be kind of a fly in the wall in that situation and see how they worked it all out. More and more examples of the same stuff here. I don't think I can read any more diffusion papers, guys. I think my brain is maxed out. I'm leaking diffusion model stuff from my ears. There's just too much information here. But we've kind of loaded our brain with this context now. And I think it would make a lot of sense to take all this context that we've learned and try to apply it to something actually useful, something programmable. Maybe we try to make a diffusion model from scratch, but cool. Yeah, I think I'm just gonna end it there. I feel like my brain is falling apart right now. But this was by far the kind of largest and most impressive paper. Although no code, so gotta kind of hit them on that. They don't really release their code. I wish they kind of released this data set, made this model available. Yesterday's paper, the Paya, that was a lot more democratized. They release the code, they kind of show you the data sets, they give you the model. It's all MIT licensed. So despite what they're saying, the people at Stability and Google Research, they are a little bit more protective, a little bit more walled garden. They're thinking about the money and thinking about how to monetize these things rather than actually trying to democratize them. But I'll get off my soapbox. This has been a marathon of papers this week. Thank you for watching, and you guys later.